All right, so let's talk about universal gates. So a universal gate is how a gate, such as a NAND or a NOR gate, in our instance, we're going to be using a NAND gate, but how a gate such as a NAND or a NOR can be used interchangeably with a AND, a or a NOR gate. So why is this important? If, say, we are given this equation here, we can take this given Boolean equation, we can convert all of its ands, its ors, into the respective NAND equivalents. We can simplify all the double NOT gates after that, and then finally convert to a more simplified and or circuit by the end of this. So let's go ahead and dive into the process. First, we will be converting, let's see here. We're going to be converting everything just to its respective ors, its respective ands, and so this is what we have here. So as you can see, we have A being ORed with B's complements, which is here, A's being plugged in there, B complement is there. We have A and we have A being ANDed with C knotted and all that being knotted together. That's here. A, C knotted, everything being knotted after that. We have those two being ANDed together, and you can see both those inputs going into an AND gate here. And then finally, we have all of that being ORed with B here plus C here plus all that at the end being knotted together. And that's, like I said, being ORed together. So from here, what we want to do is take all these OR gates and AND gates and put them into their equivalent NAND gates. So this is what we have here. So as you can see, this is the OR equivalent. So we have the OR gate here, and this is the NAND OR, where we have two NOT gates before a NAND gate, and that is perfectly representative of the OR gate. For the AND gates, for example, like this one, let's take this for example, what we would do is we would have a NAND gate and then have it complemented afterwards, and that is 100% equivalent as well. We do that for all the other gates, and we get this. And as you can see, we have a lot of NOT gates here. And for example, if we have two NOT gates like this one here and this one here right after one another, they can actually just be canceled out. So for the final process, we cancel out all the double NOT gates and are left with this most simplified version. So from here, what we can do is compare and see if this is actually equivalent to this. So I'll go ahead and open up where it's just these two. And we're going to do a circuit analysis of them both to see if we get the same equivalent Boolean equation. So you can just go up to project here, analyze circuit. And as you can see, we have output Q, which is representative of our very first circuit here with just all ands and ors. And then here Q2, we have, which would be the same circuit, but with all the NAND equivalents. So they don't look similar right now, but they will be. We can take our minimize option here and select Q, and we can see that we have this equation here. B complement being ORed with A and C ANDed together. So I'm going to go ahead and set as the expression for that. Do the same for Q2. Set as expression, and we can see them side by side now. they are exactly the same. We have B being complemented, and that is both being ORed with A and C that are ANDed together. So we could see Q and Q2, these two are exactly equivalent. Okay, so from here, we can finally convert into the AND OR circuit, the most simplified circuit of this. So again, I'm going to go to Analyze Circuit. I'm going to make sure that this is as simple as possible expression, and I'm going to build this circuit here. And we're going to show what its AND OR equivalent looks like. Here. So we have A and C being ANDed together. And then we have B knotted, and that is being ORed with this AC ANDed together. And that is the most simplified AND OR circuit from the NAND equivalence circuit that we had built from this complicated Boolean equation. Thank you so much for watching. That is all.